Welcome to our presentation. Our group's name is Akshay Patra. So this is a Sanskrit word, which means unlimited container. We found it a very beautiful name for our team. And bonus, there is an Akshay in our group, so it's all the more fitting. I'm going to start with a short table of contents. First, I'll present our team, the scenario, so the problematic we had to deal with, the research we did, and finally the proposed solution we ended up with the design, the problems, the advantages, and the disadvantages. And in the end, we'll look through some next steps. So first, the team. Over here in this picture, you can see I am Nitya Rajan. There is Akshay Mahale, Aniro Ditaji, and Jahan Al-Sawaf. We are half in Switzerland and half in India, and we're also half high schoolers, half university students, so it was a really lovely balance. The people who are not visible on this picture are our mentors, but they helped us enormously, so we would like to already thank them. So speaking about this scenario now, we want to go to the moon, right? But actually, when we go to the moon, there's one thing that we need a lot of, and those are containers. We use them for literally everything, like everything. But they probably won't look like leather bags. So what will they look like? Well, to determine that, we need to do some research. So what better way to start researching than to look at what already exists? This is the container that went on Apollo. And as you can see, it looks like a bit like a aluminium suitcase. It's rather bulky and it only uses aluminium as shielding. Why shielding? So lucky for me, the group before explained what radiation is and how there is a lot of it on the moon. But rather than protecting this, so this box is to contain samples, right? These samples are radioactive. That means instead of protecting the astronaut from outside radiation, our main goal was to make the scientist who then arrives at these samples be safe from the moon rocks that have a lot of radiation on them. So we basically wanted our box to be radiation proof, which this box, although aluminium does have shielding properties, isn't fully. But we do get a hint from it. Aluminium, it's actually a really great metal because for its density, perhaps it's better visible on this graph, for its density, this strength that aluminium has is incredible. It's stronger than steel actually. So that's why we immediately knew that for stability, we would use aluminium for our container. We were mainly focusing on two aluminium alloys, aluminium 6061 and aluminium 7075. But there was another thing that we really needed to focus on, and that was the radiation shielding. So we did a lot of research to find out what the optimal radiation shielding would be. We wanted something lightweight, something that is commercially available, and we found a lot of solutions, but each one of them had their flaws. So in the end, after a lot of elimination, we decided on lead sandwich between aluminium or bismuth trioxide, which I will go into further depth later. So what is our proposed solution? As we said, we ended up with aluminium and lead sandwiched in between this aluminium. So why lead? Well, it is firstly the gold standard already in radiation. Like it's used in hospitals to shield you from X-rays. It's really used a lot. Also, it is commercially available and cheap, and that is a huge advantage. However, another disadvantage is that the disadvantages are that lead is really heavy and it's also toxic to humans, but only if we come into direct skin contact with it. So now for our design. To best use the properties of lead shielding while still trying to stay in a reasonable weight, we proposed a design that has 3 layers. This is the first layer. It is the, we call it the medium box because it is in the middle of 2 different boxes. As you can see, it has a lead, whoa, my bad. Whoa. It has a lead layer inserted in the middle, and sandwiched around with aluminium, so we won't come into contact with the lead. This is a cross section, that's why you can see the lead, but it's actually not open. Next, we have the outer container. So this is actually really big. It's 3 meters in diameter to 7 meters in length. And this is because one requirement was that our thing needed to be external to the habitat. So this is basically like the home for the box, but it is made out of aluminium and doesn't really have any lead shielding. Finally, this is the most important part. It is our sample storage. So this is a honeycomb structure looking thing because it will go into an aluminium honeycomb structure in the medium box that will give it a lot of stability. And to better explain what I mean by that, I'd like to show, will it work? A link with our, I kind of forgot about this, I'm sorry. Would it be okay if I sign in, or should I just skip this part and show it later? Because, yeah, I totally.
It's going to take a couple of minutes. I think you should skip and you can place it on the Discord channel. That should be okay.
Yeah, okay, I will do that then.
I'm sorry, even I don't have an account and have not signed into it.
Yeah, no, it's no problem.
Okay.
It's my bad. I should have thought of it. Then maybe we can go back to the PowerPoint. Can you?
Yeah, sure.
Thanks. Thank you, and sorry about that inconvenience. But the idea basically is that we have just, if I can give you a small idea of what, oh, I don't have control over the screen anymore. Oh, I do. It's basically that the medium box goes into the large container and the sample storage that looks like a hexagon goes into the medium box. So there will be many layers of lead during all these boxes, which will provide adequate shielding. We calculated that. There are a lot of formulas that you can use to calculate that. The biggest problem we had while really researching this was time, of course, but there is really very little research material that we found just by surfing the internet for radiation shielding, since none of us are really in that area. We really learned a lot, and we think it's an area that could really use a lot of progress still, because in a NASA document we saw the understanding of the effectiveness of shielding materials and amounts is incomplete, really. What are the advantages of our proposed solution? Well, first off, it's actually pretty cheap. So for 2 boxes, which are half a meter in length, breadth, and height, we and 20 sample storage units, it'll only cost 1,180 and will provide a very sturdy box with effective shielding and great protection for all samples. We also think that it ticks off a lot of the required criteria in the sense that it is new. It may not be using some crazy innovative new materials, but that is because we also wanted something that has already been verified. It is relevant because, as I've said, it's really necessary that we have something like this that will shield. Contributions to scientific value, perhaps there we can have a little bit extra work, but project cost is really good, and feasibility, I think it's totally feasible. And most importantly, we had great fun during this hackathon. Disadvantage, it's heavy, as you would expect. Both boxes together with all sample storages would be about 425 kilos. But on the moon, that's only 70 kilos, which is maybe not that bad. However, as I was saying before, we were still thinking about bismuth trioxide. So bismuth trioxide glass is actually something that was discovered last December. And it's showing really promising capabilities in shielding, as well as being lightweight and low cost. And perhaps if this does prove to be the wonder material that we hope it is, it could be a great alternative to lead, definitely minimizing the weight of our box. So for the next steps, we want to and we will do everything to ensure that this box, Akshay Patra, can go to space and serve humanity and teach us so much more about the moon, because we can only learn about it if we get samples. And perhaps the most important reason why you should adopt us, Space Doge likes us. It's a very good reason. then, thank you for your attention. And do you have any questions? And once again, sorry for the mix up with all of the CAD model and stuff. I will
So
send it.
it's okay. That's why we try to prevent these, right? That's why we always say we have certain ways we want to do the presentation style, and it might seem confusing at first, but technical details can be technical errors can be quite challenging. But otherwise, yeah, it's great job. Okay, great presentation. The flow is very good. And at this time, we will open the floor up to the mentors. Do the mentors have any questions? And then, of course, after that, we will follow up with the other participants' questions.
Yeah, I have a question.
Yes.
Can you hear me? Yeah. You might have said that, but what's the size of the container in the end?
The biggest container?
Yeah.
That is 3 meters in diameter and 7 meters in length. So it is huge.
Okay.
But we don't just plan to house storage materials in it. We also, as in sample storage, we plan to also put food, etc. in it, just that we didn't really go into that direction.
Okay, thank you.
Hi, thank you for your presentation. And I'd like just to say this was a very nice narrative. So congratulations on this presentation again. Concerning the weights, so you've mentioned the weights on the moon, but as you probably know, everything that goes to the moon has to leave Earth. So the weight would actually be a problem if you have to put it on the rockets and you would need a lot of fuel. So do you think, have you thought about any ways to mitigate this problem? Do you think?
Yeah. So actually, perhaps I didn't talk about this before, but when I was speaking about the weight, here, this picture you see is actually not the weight of our prototype. It is the weight of what went to the moon all the way a long time ago. I don't know what exactly the years are, but basically, we have the shell, which in their case is 500 kilos, which we already tried to optimize by just finding the right ratio between aluminium and lead. And therefore, we really tried to keep it under 500 kilograms. This is in kilograms, by the way. So for that reason alone, we think that if they could do it then, we can still do it now with 400 kilos, 420.
Okay, perfect. Thank you.
Any other questions?
Is there questions from anybody? Okay, then I guess we're gonna.
Hello. Yeah. Hi. I just had a question.
Yes.
Have you analyzed about the stress that is the stress analysis of the metal? Like, will it lead to cracks in the metal or stuff like that? Have you analyzed that stuff?
So I think I'll give this question to Akshay. He was the one who was really focusing on that area. Akshay, you want to take over?
Yeah. Actually, what we have using, like, we're trying to make like the outer shell. You're asking about the outer shell container or like the smaller one, the medium container?
Probably you could tell about both.
Yeah, actually, the outer container we're using like aluminium, like a honeycomb structure. So what will we have because the lot of like the bending is occur just because of the in the shell. So we try to make it the honeycomb structure. So it will be try to reduce the like bending movement during the spirit. So because it will be the cylindrical shape. So the aluminum we have used there, and for the inside the smaller container, so we're using the aluminum itself. So we have considered the every stress analysis, and it's we thought about the selecting the aluminum series. So we consider the 6000 series. It's better than 7000 because it's having the high working like machinability, means we can weld properly with the help of the 6000 series. When it comes to the like 7000 series, if you want more strength, we can go forward for 7000 series, 7075 series. Yeah.
And perhaps to add to Akshay's answer, We could also justify our choice with the past, because aluminium, especially I think this series, is used like a lot in space already, which would just come to show that it can withstand a lot. So yeah, perhaps history itself can justify a bit.
And about the lead embedded between the aluminum layers, is that safe enough and stable enough not to have cracks in it and breakages?
Yeah, we judge by, first of all, if the lead does get cracked, it will not be catastrophic. But second, with the thickness that we chose of the structure, and also the fact that there is a multi-layer system, we will, even if that we already are making sure that the most important layer, that is the layer that is closest to the sample, is shielded by a lot of different layers, and a lot which will all take a lot of stress impact. And I think that is really how stress will not affect too much our solution. And either way, we chose the thickness of the aluminum as such that it will be optimal.
Okay, thank you so much.
Okay, now we're gonna have a break for 20 minutes.
Thank you for your attention once again.
Thank you.
Thank you very much for your presentation. See you in a bit.